One of the present generally conspicuous physicists, Michio Kaku, has talked about his assessment concerning this issue. Kaku, known for his astounding contributions to the field of physics, has recently acknowledged that the James Webb Space Telescope has discovered 6 monstrous, inestimable systems that researchers once thought couldn't exist. These appraisals have the potential to open up new perspectives in our ongoing appreciation of the universe. It is therefore entrancing and worth observing out for these changes. Kaku is an extraordinary figure in the scientific field. A physicist of American and Japanese heritage, he is viewed as an expert in both traditional exploratory physics and quantum mechanics. Unlike some more moderate and suspicious researchers, Kaku doesn't belong to that group. He has been open to the astonishing new findings of the James Webb Space Telescope mission. We are grateful that this distinguished researcher has decided to end his silence and directly share what can no longer be denied. The excitement and enthusiasm of the famous physicist are clear in his remarks on the discoveries made by the James Webb Space Telescope. Given that this has been the feature that has sparked his interest, join us to explore the implications of Michio Kaku's disclosure of these 6 gigantic inestimable systems. Kaku is a researcher who has always been able to contemplate new theories throughout his life. He understands that Einstein's theories of relativity and Newton's laws are insufficient to capture the full complexity of the universe. Kaku recognizes that the discoveries of the new telescope could potentially improve the scientific field. Although many of his colleagues have not been able to adopt this view, it is causing concern and restlessness among defenders and critics of quantum mechanics. Nonetheless, this only invites laughter from Kaku. The JWST has uncovered the discovery of 6 gigantic universes dating back to the earliest epochs of the universe. Each of these grandiose systems contains more stars than our own, despite having formed only a brief time after the Big Bang. The group of cosmologists who made the discovery has named these magnificent systems universe breakers, as their presence would change our entire understanding of the universe. Something here no longer fits with the theory of the Big Bang, which tells us that the universe was a disaster area after the initial event. The first solid objects took hundreds of millions of years to form, and it took even more years for objects to reach a useful density and produce light. The development of complex structures like galaxies should have occurred much later. Some of the newly found systems surpassed the Milky Way in size, and their immense brightness shows that they were likely forming many new stars every year, whereas our galaxy forms stars only intermittently. It remains unclear exactly when the first galaxies formed. Scientists have been unable to determine this until recently. The only thing that is clear is that initially, there may have been only single stars or groups of stars that eventually came together to form progressively larger structures, ultimately leading to the formation of dwarf galaxies, which merged and gradually evolved, as previous theories had predicted. Incredibly massive and large galaxies could not have existed at that time, which raises the question of whether the universe is much older than previously acknowledged or whether complex toroidal structures were formed much earlier than anticipated. This situation is challenging for conventional science, which still struggles with this model. Moreover, some areas of physics have strongly rejected this discovery, pointing to potential errors in the age computations. Kaku was aware of this and had this to say: "There are many instances of old and misleading theories that persist due to the prominence of certain researchers. Many of these theories were eventually disproven when fundamental research revealed their false ideas. Therefore, the key work in any science, particularly in physics, rests with the experimentalists who maintain the integrity of the research. As a matter of fact, on Earth, we have virtually no information on the true origins of the universe." The Big Bang theory was formulated in 1927 based on observations of the universe's expansion. This led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to imagine a universe with a beginning and an end. The idea of a universe that had always existed and was infinite in time was beyond human imagination. Even today, scientists still face challenges in understanding it. However, it is crucial to reconsider these possibilities. These new insights don't fit at all with what scientists have relied on for years in the Big Bang theory, but science has shown time and again that reassessment and openness to groundbreaking ideas are critical components of the scientific process, just as much as the validation of specific theories and observations. When Einstein was a young man, It was believed that the stars and planets were firmly fixed in the universe, and these particular structures occupied a defined space. However, we now understand that everything in the universe is in motion. Planets orbit stars, stars move within their galaxies at various kilometers per second, and entire galaxies move rapidly through the universe, the fate of which we cannot yet predict. Today, scientists are challenged to accept uncomfortable findings, and it is understood that theories are not simply assumptions or fundamental truths until they are thoroughly tested or confirmed by accurate observations. The idea of the Big Bang emerged from the confirmation that galaxies are moving away from each other, and this distance is relative to the distance from Earth. This observation, known as Hubble's law, suggested that the universe was expanding. For a long time, parts like cosmic microwave background radiation and the red shift of light from distant galaxies and other cosmological structures seemed to support this theory. However, it is important to remember that in the past, people who believed the Earth was flat and that the Sun orbited the Earth also had this kind of evidence for their doubts until events or technological advancements provided a clearer and more accurate picture. Right now, we are seeing a similar situation. Scientists expected the new JWST to confirm the assumptions associated with the Big Bang, but instead, they have encountered the 6 systems that appear far too advanced for their age. This reminds us that science is continually evolving and that scientists must be open to new discoveries and reconsider existing theories in light of available evidence. Researchers use redshift as a tool to determine specific measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to each other. To understand this, you can imagine stopping and listening to a car coming towards you. As the car approaches you, you hear the engine get louder. However, once the car passes you or moves away, the engine sound changes. This is because the sound changes as the car moves. The same is true for light. When a light source, such as a distant star, moves toward us, the light we see shifts toward blue tones. Conversely, when the light source moves away from us, the light shifts toward redder hues. This phenomenon is called redshift. Physicists have converted redshift values into speeds and distances for measuring sums in the study of the universe. However, it is important to note that small errors in these measurements can have huge implications. The measurement techniques previously used are now under review, and the results that experts will arrive at concerning the latest discoveries related to our universe are intriguing. It is essential to consider whether these results are really based on redshift errors or whether some experts are simply denying the facts. This is a question that requires intensive evaluation and careful scrutiny of the data and techniques used in the study. As scientific inquiry progresses, the discoveries made by instruments like the James Webb Space Telescope often challenge our assumptions about the universe. The new discovery of 6 massive inestimable systems dating back to the early stages of the universe is one such example. These systems, which defy conventional hypotheses of galaxy formation, raise significant questions about the timeline and processes associated with the development of large structures. The James Webb Space Telescope, a replacement for the Hubble Space Telescope, is equipped with cutting-edge technologies that enable it to peer deeper into space with exceptional clarity. Its ability to detect light from the far reaches of the universe provides space scientists with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive galaxies challenges existing models, which predict that such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond astronomy and into the realm of fundamental physics, compelling scientists to reconsider established theories about the early universe. This includes the hypothesis of the universe's beginning, which states that the universe began from a single point and has been expanding ever since. While observational evidence like the cosmic microwave background radiation and the red shift of distant galaxies initially supported this hypothesis, the discovery of galaxies that appear far too evolved for their age complicates this narrative. Michio Kaku, a prominent physicist known for his work in theoretical physics and popular science, has commented on these developments. Kaku, known for his ability to connect complex scientific ideas with public explanations, recognizes the profound potential of the JWST discoveries. Unlike some of his more skeptical colleagues, Kaku embraces the idea that groundbreaking observations should prompt revisions in scientific thinking. He has emphasized the importance of empirical evidence in shaping our understanding of the universe, highlighting that theories must continuously evolve to accommodate new information. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, there are supporters who argue that the discovery of early massive galaxies suggests a longer timeline for cosmic development than previously thought. This perspective challenges the traditional view that galaxies evolve gradually over billions of years through mergers and the steady growth of smaller objects. On the other hand, skeptics caution against discarding established models based on limited observational data. They advocate for a cautious approach, suggesting that anomalies in data interpretation or measurement errors could explain the surprising findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a critical role in these key investigations. As galaxies move away from Earth, the light emitted by them shifts toward the red end of the spectrum. This effect, known as redshift, serves as a vital tool for measuring distances and determining the relative velocities of galaxies. By studying the redshift of light from distant objects, scientists have made significant strides in mapping the expansion of the universe and understanding its history. Despite the challenges and complexities involved in interpreting these findings, the discovery of massive galaxies from the early universe represents a profound step forward in our understanding of cosmic evolution. The role of the James Webb Space Telescope in uncovering these mysteries underscores the importance of continued exploration and open-mindedness in the pursuit of knowledge about our universe. The James Webb Space Telescope, JWST, has not only redefined our understanding of the universe, but also sparked a deeper conversation about the tools and methods we use to study the cosmos. With its unparalleled ability to capture infrared light, JWST has enabled astronomers to observe objects that were previously invisible or too distant to study in detail. This capacity is crucial for examining early galaxies that formed shortly after the Big Bang, as they emit light that has been stretched to longer wavelengths due to the expansion of the universe. These observations are pivotal in reconstructing the timeline of cosmic evolution. One of the most striking aspects of the recent discoveries made by the JWST is the presence of massive galaxies that appear to have formed in the first few 100 million years after the Big Bang. This contradicts the long-standing belief that large galaxies took billions of years to develop. Traditional models of galaxy formation suggest that smaller galaxies gradually merged and grew over time, eventually creating the large, complex structures we see today. The discovery of these early, massive galaxies challenges this assumption and forces scientists to reconsider the processes that led to the formation of large-scale cosmic structures. The fact that these galaxies are already well-developed and contain a high density of stars has led some researchers to propose that the early universe might have been more conducive to rapid galaxy formation than previously thought. Some theorists now suggest that the conditions in the first few 100 million years after the Big Bang were more favorable for the formation of large galaxies than was previously believed. This could mean that the universe underwent a phase of accelerated growth, possibly due to factors like higher star formation rates, increased gas accretion, or different conditions in the early intergalactic medium. Another important question that arises from these discoveries concerns the role of dark matter and dark energy in galaxy formation. While dark matter remains invisible and elusive, its influence can be observed through its gravitational effects on visible matter. It is believed that dark matter played a crucial role in the formation of galaxies by providing the necessary gravitational pull to bring matter together. However, the exact nature of dark matter and how it interacted with normal matter in the early universe remains a major area of research. These new observations might offer clues about the relationship between dark matter and galaxy formation, as they challenge our current understanding of the process. In addition to these larger questions, the discovery of these early galaxies raises the possibility that they might hold the key to understanding the first stars. The first generation of stars, known as population 3 stars, are thought to have formed from nearly pure hydrogen and helium, with little to no heavier elements. These stars would have been significantly more massive and short-lived than stars today, and their death would have contributed to the creation of the first heavier elements in the universe. If the newly discovered galaxies contain remnants of these early stars, they could provide valuable insights into the conditions that prevailed in the universe's infancy. Moreover, the study of these galaxies could also help solve one of the greatest mysteries of cosmology, the reionization epoch. This period, which occurred about 400 million years after the Big Bang, marked a critical transition in the universe's history. During reionization, the radiation from the first stars and galaxies ionized the hydrogen gas that filled the early universe, allowing light to travel freely through space for the first time. Understanding how and when reionization occurred is crucial for piecing together the history of the universe's formation and the development of large-scale cosmic structures. The discoveries made by the James Webb Space Telescope have shown us that the universe is more complex and dynamic than we previously imagined. As we continue to study these ancient galaxies, we are forced to confront the possibility that our current models of cosmic evolution may need to be revised. Just as past discoveries have led to paradigm shifts in our understanding of physics and astronomy, so too will these findings challenge us to think more broadly about the nature of the universe and its origins. While the JWST has provided extraordinary data that will likely fuel scientific breakthroughs for decades to come, it also underscores the importance of remaining open to new ideas and theories. Just as earlier generations of scientists had to grapple with the implications of discoveries like the heliocentric model or the theory of relativity, today's astronomers and physicists must be willing to question established ideas in light of new evidence. The ultimate goal of science is not to prove preconceived notions, but to understand the universe as it truly is, no matter how surprising or counterintuitive that understanding might be. As we continue to explore the depths of space, the discoveries made by the JWST will no doubt inspire future generations of scientists to ask bigger, bolder questions about the universe. Whether or not these findings lead to a complete overhaul of our cosmological models, they represent an important step forward in our quest to understand the cosmos and our place within it. The journey of scientific discovery is never linear, but each new observation brings us closer to answering some of the most profound questions about the nature of reality itself.